All right, let's jump into problem 2 now. So this one is a multi-part problem. And so we're going to start just by talking about the system and the assumptions and the energy flow diagram. And then we'll get into each of the solutions for the individual parts. So this problem statement is a little bit long and wordy, so I'll kind of talk through it as I talk about what's going on with the system below. So let's just jump into it. It tells us here that the state of saturated liquid vapor mixture of water flowing in a pipeline can be determined with pressure and temperature measurements in the system diagrams below. The chamber is initially evacuated at state 1. So the chamber is right here, and it tells us that it is initially evacuated, like it says right here. So that just means that there is no mass inside the chamber initially. We have some SLVM substance flowing in this pipeline, but this valve is closed, so none of it is going into the chamber. Then the valve is opened, and the SLVM substance starts to enter the chamber until the chamber pressure equals the pipeline pressure. So at state 2, this valve is opened and mass is allowed to flow from the pipeline and start to fill up the chamber until the pressure in the chamber is equal to the pressure in the pipeline. Then the valve is closed and the pressure and temperature are measured at state 2. So then after all the mass has flowed into the chamber, the valve is closed again and there is a pressure and temperature measure taken, and we have these values here. It also tells us that the chamber is considered to be adiabatic for the process from state 1 to state 2. So as the mass is flowing into the chamber, there is no heat transfer going out, in or out of the chamber. But then the chamber is slowly cooled to a final temperature of 160 C. So after the valve is closed again, there's just some heat transfer that occurs from the tank to the surroundings in order to cool it from 200 C down to 160 C at state 3. So that's what's going on in these processes. So let's start by sketching out the system and the mass and energy interactions here on the next page. They give us this diagram. So for our system here, we're going to want to do a control volume type of analysis focusing on the tank. So I'm going to draw my system boundary around the tank here, and that's going to be our system. I'm just going to write tank control volume because we're not focusing on some amount of mass in this case like we do in control mass problems. We're focusing on the volume of the tank here and what happens across this boundary of the tank with mass coming in and heat transfer going out. So all we have to draw for our mass and energy interactions are those interactions with the tank here. And that's just going to be some mass flow rate from 1 to 2. So I'll write that as m dot from 1 to 2. And then a heat transfer from 2 to 3. So that will be Q from 2 to 3. Remember, it said that this process from 1 to 2 is adiabatic, so there's no heat transfer during that process. So the only heat transfer we have to worry about is the one from 2 to 3. And if we think about the system, there's no work terms that we have to worry about because we're going to assume that the walls of this tank are rigid. So as long as these walls are fixed and they're not moving, there's no work happening. It's not like a piston cylinder problem, and there's no other forms of work happening besides boundary work. So since these walls are fixed, there's no boundary work, and we have no work throughout the problem. So that's all we need for our system diagram. And so we can just write some assumptions. So first, we've talked about a couple of them already, but we said that the heat transfer from 1 to 2 is going to be equal to 0 because that process is adiabatic. Then also, like we talked about, we're not going to have any work in this problem. So I'll just say that the work from 1 to 2 is equal to the work from 2 to 3, which is just going to be equal to 0. I'll just write rigid here, but you can write whatever you want to indicate that there's no work happening in this problem. Another assumption that we like to make when we have inlets and outlets is that we have 1D, one-dimensional uniform flow at the inlet. Which just means that all of the mass coming in here is coming in nice and uniformly. Then we are going to say that we're going to neglect any changes in kinetic and potential energy. Delta KE equals delta PE, which is just equal to 0, because we're not given any information about any changes in kinetic or potential energy. I also like to usually write down, whenever we have any sort of supply line or something, some large reservoir or anything like that, I'll say that we have constant properties in the pipeline. Kind of running out of room here, but constant properties in the pipeline, which means that we have some mass going into the tank here, but since we consider this supply line to be a large supply line, the mass that comes into the tank is not going to affect the pressure or temperature of the supply line itself. So the properties of the supply line are fixed because this amount of mass that flows into the tank is small compared to the amount of mass that we have in the pipeline here. So I think that's a good list to start. And now we can move on to part A. All right, so part A says, briefly explain why only pressure and temperature measurements in the pipeline will not determine the SLVM state of the water in the pipeline. So what they're asking is, even if we know the pressure and temperature here, why can we not determine the state of the water in the pipeline? And the reason is because we are in the SLVM range. And we need to remember what the SLVM range actually means. But if we only have pressure and temperature in the SLVM range, we can actually have a variety of states. And I think an easy way to see this is by just drawing out a PV diagram or TV diagram or whatever kind of diagram you want to draw. If we have pressure and then some other property like specific volume, in the saturation region we'll be under a dome here. And so if we have a fixed pressure and temperature, maybe our Pn is somewhere right here. So the line of constant pressure would be across. And then we have an isotherm, remember, for temperature coming in like this. And so maybe all along this line is our Tn. And so they intersect in this region under the dome in the SLVM region. So all along this red line here, we have the same pressure and temperature. And this is our SLVM region. So if we know the pressure and the temperature, we don't know the exact state because we could be anywhere along this line. We could be here and we could also be over here or anywhere in between. We don't know if we only have pressure and temperature. If they gave us one more property like specific volume or anything else like that, then we could fix the state specifically. But we're not able to do that with just pressure and temperature. Another way to see this, if you like the charts, is by looking at the SLVM charts. You're given a pressure and temperature in the SLVM region, but remember our properties here can vary from here on the liquid side all the way over here with the vapor side, and they can be anywhere in between. So for just the pressure and temperature, we don't know the full state. So that's the answer. I'm just going to write it out like this, but you can write it out any way that you want in order to communicate that point. I'll just say in the SLVM region, properties can vary with quality. And so what that means is we would need one more property would be needed to determine the state. So again, you can write it out however you want in order to communicate that point. But when I say that properties vary with quality, all that I mean is we can have a range of properties here along this line, but if we know the quality, then we can fix the state at a specific point here. But that would be the answer to part A. Just think about how you would write it and make sure you're communicating this point, that for only knowing the pressure and temperature in the SLVM range, we don't know specifically where we are along this line. Part B says, determine the quality of the mixture flowing through the pipeline if the chamber measurements are T2 equals 200 C and P2 equals 7 bar. So they're telling us here at state 2, we have the pressure and temperature measurements of the chamber. So we have the information here, but how does that help us relate to getting the quality of the water in the pipeline? Well, if you remember from our last part of the problem, we said that with only pressure and temperature of the pipeline, we can't determine the state, right? And our conclusion was that we need one more property. We need one more property in order to determine the state of the mixture. So the reason that we are interested in the information at state 2 is that we can use a first law energy balance over our system, which is the chamber, and with that we can get one more property at the inlet, and that will be the enthalpy at the inlet. And we can do that by looking at the mass coming into the tank compared to the changes of energy of the stuff in the tank there. So we can use this information here in order to get our last property that we need in order to find the quality of the pipeline here. So that's going to be our approach. So to start, like we said, we're going to apply first law across our system here. So let's scroll down to first law in the equation sheet and simplify it down. So here is our first law equation, and we're only going to want to look at the process from 1 to 2, at least to start. We don't want to apply this over our whole process, only the process from 1 to 2. So we will have some mass coming in for that process, but we don't have any mass going out, so we are going to cross out this term. And also we're neglecting any changes in kinetic and potential energy, so those terms go away. And then for our process from 1 to 2, we have an adiabatic process. So remember, Q from 2 to 3, we do have some heat transfer there, but from 1 to 2, that heat transfer term cancels out because it's adiabatic, and we also don't have any work during that process. So we're left with just this m dot h in term, which is going to be our properties at the inlet. That's how we get our final h value there. And this dE dt of the system term. So if we just integrate both of these terms here, we get a version that will look like this. When we integrate this time derivative, we get a delta. So I'll say E2 minus E1, and that's going to be equal to M in the total mass into the system, right? The dot will go away for the M dot, times H at the inlet. And remember here we are neglecting any changes in kinetic and potential energy, and we usually write E as equal to the internal energy plus the kinetic energy plus the potential energy at a given state, but these kinetic and potential energy terms will cancel out, and so what we're going to be left with is U2 minus U1 is equal to M in times H in. And for these U terms, remember the capital U term is really a mass value times the specific internal energy. So we can also just write this as M2 U2 minus M1 U1 is equal to M in H in. And so this is our final form of first law. But we need to remember something. It told us that at state 1, the chamber was evacuated, right? Because we're looking here at this process from 1 to 2, and at state 1, there was nothing in the tank, so this mass value is actually going to 0. So all that we're left with, if we cross out this term, is M2 U2 is equal to M in times H in. But here we can simplify it even further because our mass in is just going to be equal to our mass at state 2. All of the mass that's coming in is just going to be the total mass at state 2 because we didn't have any mass at state 1. And you can see that really quickly just by simplifying out our conservation mass equation down here. If you want, we can cross off this term. And if we integrate these terms here, this just becomes m2 minus m1 is equal to m in. But again, our m1 term goes to 0. So we just see that m2 is equal to m in. Sorry, it's getting a little messy here, but that's the result that we have. M2 equals m in. So we can simplify this even further because that term will cancel out. And so the final final result that we want here is that our U, our internal energy at state 2, is just equal to our enthalpy at the inlet. So now we finally have our final state, or our final property that we need in order to fix the state at the supply line, because this enthalpy at the inlet is going to be the same as the enthalpy in the supply line. And that is just going to be equal to our internal energy at state 2. And we can find that just from our tables. So this is the result that we want. I'm just going to write this up in the equation section, but you would want to go through this whole derivation of all the processes yourself. So make sure you don't just write this final result there, but you go through the derivation yourself. But in our equation section, this will be our desired outcome of our first law analysis, is that U2 is equal to H in, and we get that from first law. So we can find these properties because we can find U2 directly from the steam tables. And we need to look at the superheated vapor tables because here at 7 bar and 200 Celsius, we are outside of the saturation region that you see here in the SLVM tables, because our temperature here is higher, our temperature at state 2 rather is higher than the saturation temperature. So that means that we should be in our superheated vapor tables. And you can see right here, this is a cut of the superheated vapor tables. And we see that we have a combination for 200 Celsius and pressure equal to 7 bar. And so we want the internal energy value here. This is our U2. U2 equals 2635.3 kilojoules per kilogram. And like we said, that should be equal to our H2, which will be somewhere in between these two values for enthalpy in the saturation region. So for this, for our H2, we want to use these SLVM tables because we are in the saturation region here. But here in state 2, we are in the superheated vapor region. So SLVM for the pipeline, but superheated vapor for the tank. So make sure you understand that. But we should be somewhere in between these two values here. And the way that we're able to find the quality by having this value, which is also equal to H2, is by using the equation for quality that we find in the equation section. So if we scroll down, we have an equation right here that we can use to find the quality at any state, as long as we have some property of the mixture. And for us, that is going to be our H in. So we can write this equation down up top in our equation section. So I will write here, we are going to choose H for our Z. So H at the inlet should be equal to X at the inlet times HG plus 1 minus X at the inlet times HF. And we can just rearrange this in order to solve for our X in, because our H in, like we said, is just this value right here. Sorry, I should have written H in here. So this is our H in value that we can plug in here, and then these HG and HF values we can just get from the table up here. So let's start to simplify that out in our solution. So again, we'll get H in is equal to X in times Hg plus 1 minus X in times Hf. And maybe you have memorized a different form of this equation that already is the solution when we're solving for X. But if not, you can get to it pretty quickly just by doing some rearranging here. So we just distribute the HF to the two terms here, and this right side becomes X in times Hg plus HF minus X in times HF, right? Because we just are distributing this to the 1 and to the X in, like you see here. And then we can move this term all the way over to the other side, and then we can consolidate the X on this side. So that becomes H in minus this HF value that we're moving over. HF should be equal to, and then we can consolidate the X in on the other side because these two terms both have X in, times Hg minus Hf. And so we can rearrange to solve for X in by just dividing everything by this term here. And so finally we get X in should be equal to H in minus Hf divided by Hg minus Hf. And like I said, we can just get all of these values from the table. So if we plug things in, we will get X in should be equal to our H in value was the one that we found up here, 2635.3 kilojoules per kilogram, minus our HF value comes from the fluid or the liquid side of enthalpy, which is 697 kilojoules per kilogram, 697 kilojoules per kilogram, all divided by our Hg, which comes from the other side of the table right here, 2762.8, 2762.8 kilojoules per kilogram, minus again our HF, which is the same in the numerator here, 697 kilojoules per kilogram. And so just plug this into your calculator and you should get that our X in is equal to 0.938. So that will be our final answer for the quality of the pipeline, 0.938. All right, let's give part C a try now. Hopefully you tried to do it all the way through on your own. It is pretty long, so buckle up and let's just get after it. So part C asks us to determine the entropy generation per unit mass for the water from state 1 to state 3. Take the boundary temperature to be the final temperature T3 and report our answer in kilojoules per kilogram Kelvin. So this problem is a bit long because we need to do a lot of different things, evaluate a lot of different properties. And we're after here the entropy generation per unit mass from state 1 to state 3, which is basically sigma from 1 to 3 should be equal to sigma from 1 to 2 plus sigma from 2 to 3. Right? There's going to be some entropy generation in this process from 1 to 2, and then again there's going to be some more in this process from 2 to 3. So we'll need to apply second law 2 times, once to get sigma here from 1 to 2, and once to get our sigma from 2 to 3, our entropy generation term there, and then we can add those together in order to get the total entropy generation for this process. So we're going to need to apply second law. Let's just scroll down and look at it. So this is our entropy balance equation right here. We'll need to apply it twice, but we can simplify it down a little bit for both cases because we know that we don't have any m dot coming out. So this term will go to 0. And then this term will go to 0 for 2 to 3, but not for 1 to 2. So let's focus on 1 to 2 first. For 1 to 2, if we simplify this, we will still keep this m dot in term, because 1 to 2 is when we're filling the tank up. But we can cross off this q term because we have an adiabatic process from 1 to 2. And so we're left with these terms, and we can just integrate all of them here. And then we will get the simplified form, I'll write it up here, of m2 s2 minus m1 s1 should be equal to m in times s in plus our sigma term from 1 to 2. So our dots here go away, and then our ddt becomes a delta, and we can write that out as m2s2 minus m1s1. And remember from the earlier part of the problem, we can cancel off this term because we don't have any mass inside the container at state 1, so m1 is equal to 0. And furthermore, we remember that m in should be equal to m2. If we want, we can see that through our conservation of mass equation, right? Because we don't have any mass going out. And so if we integrate these terms again, we get m2 minus m1 equals m in, but m1 is equal to 0 here because the tank is evacuated at state 1. So these terms here are equal, and we can just divide everything by that mass, including this sigma term. And if we do that, we just get an S2 minus S in should be equal to sigma from 1 to 2, since we're just moving this m dot in over to the other side. So this is the version that we get from 1 to 2. For 2 to 3, it would be slightly different. And maybe I'll just do that right now so that we can move on and don't have to come back down here. I'll move this one up a bit. This will be from 1 to 2. And then from 2 to 3, it will be slightly different. I'll box this real quick. And so from 2 to 3, instead, we don't have any mass coming in now because the tank is already filled and the valve is closed. Again, we don't have any mass coming out, but now we do have to worry about this heat transfer term. So we are going to write this out. If we integrate all of the terms again, we'll integrate heat transfer term, entropy generation term. We'll get now m3 s3 minus m2 s2 should be equal to a q over TB plus that sigma from 2 to 3. We can realize here that the mass at state 2 is equal to the mass at state 3 because we're not changing mass. So we can just divide out all of the terms by mass, and then these will become on a per mass basis like it asks us to do. And so if we do that, then we can just see, if we rearrange this equation, S3 minus S2 minus Q from 2 to 3 divided by TB should be equal to sigma from 2 to 3. So this is the version that we can use from 2 to 3. But we don't have this heat transfer term yet, so we need to get that. And the way that we need to get that is by using our first law equation. So you can see already how things are starting to become complicated. But we want to do that first law equation, apply it over the process from 2 to 3. So we can do that. Again, there's no mass coming in or out from state 2 to state 3. So we can cross off those terms. And there's no work from that term, right? 2 to 3 is just the cooling of the tank. So we're left with our heat transfer term and our change in energy term. So if we integrate both of these terms, we just get from 2 to 3, I'll write it down here, m3 u3 minus M2U2 is equal to our heat transfer from 2 to 3. The dots go away, and this becomes a delta. And again, M3 should be equal to M2 because mass isn't changing. It's just cooling down from 3 to 2, or from 2 to 3. So if we divide through everything by mass, we get the term, or we got the expression, U3 minus U2 is equal to our specific heat transfer term from 2 to 3. Okay, so this is the final piece of the puzzle. We have our Q23 that we can plug into here. But we need to evaluate all of these properties. We need to evaluate S2, Sn, S3, U3, and U2. So we have our work cut out for us in order to get to these entropy generation terms. Some of them we can get easily from the table. Some of them we have to employ our quality equation. But I will write these equations up in the equations section just to make things easier. So we get U3 minus U2 should be equal to our Q from 2 to 3. And then we get our S2 minus Sn is our sigma from 1 to 2. S2 minus Sn should be equal to our sigma from 1 to 2. And finally, we get that our S3 minus S2 minus Q23 over TB is equal to our sigma from 2 to 3. S3 minus S2 minus Q23 over boundary temperature should be equal to our entropy generation term from 2 to 3. So that is our approach, and that's what we need to do in order to get these two terms and then add them together for our total entropy generation. So we just need to get into it. And so let's start by evaluating our heat transfer term here, because we'll need that for later. So again, we just need our U at state 3 and our U at state 2. So remember, at state 2, maybe I'll write it out here so that we don't get confused. Our state 2, we are in the superheated vapor range. That's the one before that we used this table here because we're at 7 bar and 200 C, like we see in the superheated vapor table here. At state 3, though, we might not be. We don't know initially off the bat. They only give us the temperature, but we need to figure out what state we're in from a different method. And the way that we can do that is by realizing here that we have a rigid tank and we are not changing the specific volume from state 2 to state 3. So rigid tank, we know that the volume is fixed, the total volume. I'll just write this out here. So the total volume at state 2 is equal to the total volume at state 3 because the total volume of this tank is not changing. And also, from state 2 to state 3, the mass isn't changing. So M2 equals M3 because there's nothing coming in or out here. And then we know that specific volume is just total volume divided by mass. So if V2 and V3 aren't changing and M2 and M3 aren't changing, then we'll see that our specific volume at state 2 is equal to our specific volume at state 3. So our specific volume at state 2, again, remember here at state 2, we're in the superheated vapor range, so we can use this table. So this will be our value for V2 and also V3. Now, the only information we have about state 3 is that we are at 160 degrees Celsius. So we have this third table that we're bringing in for the saturation table at 160 Celsius to check, is our volume here for V3 in between the values here in the saturation table? And we see that it is because we're in between this value here of 0.001102 and this one of 0.3 0.0678. So this value is in between those values, and that means that we are in the SLVM range for state 3. But we're at a different set of temperatures and pressures than we're at for the supply line. So these are different tables, but we will be in the SLVM range. Okay, so that is to say that we can find the value for U3 by using our SLVM tables and our quality equation based on this fact that we have the specific volume. So let's start by computing the quality using our quality equation. Remember in the past, or in the last part of the problem, we rearranged the quality equation. I'm just going to write that rearranged version here. X3 should be equal to, now since we have V3, we're going to use V instead of H. So it should be equal to V3 minus VF divided by VG minus VF. And these values, again, we can get from the saturation table right here. So we'll see that this should be equal to V3 is 0.3 meters cubed per kilogram minus VF, which is 0.0001102 meters cubed per kilogram. This value comes from the table right here. And then we divide by our VG, which is this value here, 0.30678. 0.30678 meters cubed per kilogram minus this same VF value, 0.001102 meters cubed per kilogram. And so the quality that we should get at state 3 should be equal to about 0.978. So we're pretty close to the vapor side, the saturated vapor side, but this will be our quality from state 3. And why is that useful? Well, we can use this quality value in order to find our internal energy at state 3 and also eventually our entropy at state 3. So that's why we need to find the quality there. So let's do that to find U3 first so that we can just evaluate this heat transfer term. So our U3 is going to be equal to, now again we can just use this same equation here, but instead of having H, we're going to have U for these different states. So U3 should be equal to X3 times UG plus 1 minus X3 times UF. So again, we can get these values from our table. X3 we just found is 0.978 times UG, which from our table is this internal energy value, 2567.8. 2567.8 kilojoules per kilogram, plus 1 minus 0.978, which is our X3 value, times our UF value, which we get from the table is 674.79. 674.79 kilojoules per kilogram. So if you plug all this into your calculator, you should get a U3 value of around, let's see, 25.8 or somewhere around there, kilojoules per kilogram. You may get a slightly different value depending on how you do your rounding, but actually I think I got something around 2526.2 kilojoules per kilogram. Okay, so that is our internal energy value, and so we can use this to apply our first law right here. Our U3 minus U2 is equal to our heat transfer term from 2 to 3. And so this should be equal to our U3 value here is 2526.2 kilojoules per kilogram minus our U2 value. This one we can get just from the steam tables. It will be right here because, again, remember, we're in the superheated vapor range for state 2 at this pressure and temperature. So our U2 value is going to be right here, this 2635.3. Okay, minus 2635.3 kilojoules per kilogram. So I got this value to be around negative 109.1 kilojoules per kilogram. So this should be our heat transfer term. That makes sense because it's negative. Remember, we should have a negative heat transfer value if we have heat transfer out of the system, which is what we expect from 2 to 3. So make sure you always check your signs. But that's what we get. And so we can use this value later in our entropy generation term for 2 to 3. First, let's do this one from 1 to 2. So we'll apply second law for the first time by saying that S2 minus Sin should be equal to our entropy generation term from 1 to 2. S2 we can get from our tables, our steam tables up here. We have that our entropy term is right here, this 6.88841. This is our S2 value, because again, we're in this superheated vapor region here at this temperature and pressure. So that's 6.8884. kilojoules per kilogram Kelvin now. Sin we need to evaluate separately because that will be the entropy value at the inlet to our tank, which is just the same entropy value that we have in the supply line. So remember, in the supply line, we're also in the saturated liquid vapor mixture range, but we use these tables instead because we're at this temperature and pressure. So we need to evaluate the entropy, which will be somewhere in between these two values of vapor and liquid, and we can do that using the quality that we just found for part B. So we can apply this quality equation, but now we're using entropy instead of enthalpy in here. So let's set that up. I'll do it just above here. So Sin should be equal to our quality in times Sg plus 1 minus our quality at the inlet times Sf. So this should be equal to Xin we found to be 0.938 times Sg, which we can get from our tables as this entropy value here, 6.7071 kilojoules per kilogram Kelvin, plus 1 minus that 0.938 times our entropy at the liquid state, which is 1.9918. 1.9918 kilojoules per kilogram Kelvin. I'm running out of room, but I'm just going to write it down here. So this should give us a value of about 6.414 0.75 kilojoules per kilogram Kelvin, somewhere around there. So we should get that our sigma from 1 to 2, our entropy generation term should be equal to about 0.47365 kilojoules per kilogram Kelvin. Okay, we're almost there. We have the contribution of the entropy generation from 1 to 2, but remember we have some portion from 1 to 2 and then another portion from 2 to 3, so we need to find both of those and add them together to get our total entropy generation term. So we just need to apply this final equation here, S3 minus S2 minus Q from 2 to 3 should be equal to, over TB should be equal to our sigma from 2 to 3. So applying that equation, we get S3 minus S2 minus Q from 2 to 3 divided by the boundary temperature is equal to the entropy generation from 2 to 3. S2, we already have that term from our table up here. That was this value right here. But S3, we haven't evaluated that yet. So we're going to need to use our quality equation again in order to find it. So that's just this equation up here, but instead of H, we're going to be using S. So I will move this down a bit and we'll solve for S3. So S3 is going to be equal to X3 times SG plus 1 minus X3 times SF. So we can get these values from the table. X3, remember we found up here as 0.978. So that's 0.978 times SG we get from the tables. So that's going to be these tables here, because remember we're in this SLBM range, but at this temperature of 160, which we see here. So make sure you're using the right tables. SG is going to be this 6.7491 value. So this should be 6.7491 kilojoules per kilogram Kelvin, and then plus 1 minus 0.978 times SF, which is right here, 1.9426. 1.9426. Running out of room for units, but they would be the same here, kilojoules per kilogram Kelvin. And so we get our value for S3, which should be about 6.6425 kilojoules per kilogram Kelvin. So this is our S3 value. S2 we can get from the table. It's up here, just this 6.8884. So this is, now we're subtracting this off, a 6.8884 kilojoules per kilogram Kelvin. And then minus our heat transfer term we found here to be negative 109. So we're subtracting off a negative here, 109.1 kilojoules per kilogram. And then for the cherry on top, we can't use the temperature that they gave us because they told us to use the boundary temperature as the final temperature at state 3, but that is in Celsius. And remember, whenever we're dividing by a temperature, it needs to be in Kelvin. So we need to do one last computation to change this from Celsius to Kelvin. So here we're going to say 160 plus a 273 in order to get that in Kelvin. So then you plug that all into your calculator and you get sigma from 2 to 3 should be equal to around, I think I got 0.00608, somewhere around there, kilojoules per kilogram Kelvin. Remember checking to match your units. Here we have kilojoules per kilogram for the heat transfer term, and then we're also dividing by a Kelvin, so we get everything in these units of kilojoules per kilogram Kelvin. And the final step is to just add them together. So sigma from 1 to 3 should be equal to sigma from 1 to 2 plus sigma from 2 to 3. So we found these terms up here and right here. So we just plug in our numbers, and we should get 0.47365 kilojoules per kilogram Kelvin plus 0.00608 kilojoules per kilogram Kelvin. And so our final answer for sigma from 1 to 3 should be somewhere around 0.4797 kilojoules per kilogram Kelvin. Maybe you got a slightly different answer depending on how you do your rounding. There's a lot of places where you could have, differences with rounding here, since we're doing a lot of different computations. But your final answer should be somewhere around there for the total entropy generation of this process.